Today I'm going to show you how to do more derivatives, and I'm going to use my toothpick. So you might want to take out your own little toothpick if you have one handy. So far I've shown you how to do derivatives of polynomials. I've shown you the product rule, the quotient rule, and derivative of a constant. That's pretty much it so far. So today I'm going to show you how to do derivatives on trig functions. So all 6 trig functions, sine, cosine, tangent, the ones you're really familiar with, and then we've got cosecant, secant, cotangent. I'm going to show you how to do all those derivatives, and they're going to have to need to be memorized. So let's get started. I think you're going to find the first 2 really cool, and then after that you're going to be like, okay, I'm done. Just tell me what the others are. So I'll do the first 2 with you. I'll do the derivative of sine x with you, I'll do derivative of cosine x with you, and then I'll just tell you what the rest of them are. So, using my toothpick, I've got y equals sine x. I've just got one period of that graphed in blue, and I would kind of look at one period of that. I'm going to do my toothpick on the sine function to look at the derivative of sine at several points along the way. And what I'm going to do is I'm just going to graph the derivative on the same graph in pink. So we've got sine x in blue. We're going to see all the slopes of sine in pink. The slopes of sine. So here we go. Ready? Let's start at x equals 0. Put your toothpick on there so that it looks like it might be a tangent line. And approximate that slope for me. The slope of your toothpick at 0, it looks like it goes right up through the first quadrant, doesn't it? So I think the slope there might be 1. Okay, so I'm going to graph that slope in pink on the same graph. Switch to pink, graph that slope of 1. All right, moving on. Slope of 1. As I move toward pi over 2, my slope is decreasing. Right? The steepness of my tangent line is decreasing. Decreasing, still positive, but decreasing. Decreasing, decreasing, decreasing. Now at pi over 2, what's the slope of my tangent line? I think the slope there is 0. So I'm going to graph my slope in pink right there. Moving on. Moving away from pi over 2, now my slope gets negative. Not very big. Bigger, 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 negative, bigger, negative, until I hit pi, and I'm going to try to touch the function only once, and what would you estimate that slope to be? I think it looks like -1. So I'm going to, when x is pi, I'm going to graph my slope in pink is -1. Still negative, not as steep, still negative. Now my slope at 3 pi over 2 is now 0. So I'm going to graph my slope in pink is 0. And now, still negative, but not so much. Still negative, but not so, no, sorry. Slope is 0. Toothpick, here I go. Positive slope. Positive, 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 steeper, 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 steeper until I get to here. And right here, it looks like my function has a slope of 1. So I'm going to graph my slope as a y value in pink. Look what the graph of y prime looks like. Oh my goodness. The slope of sine, when graphed, looks like cosine. Sure enough, the derivative of sine x is cosine of x. Isn't that cool? I'll keep the color pink again. So now let's look at our cosine graph. So we've got our cosine graph, and you're like, oh, I know what's going to happen here. It's going to be sine. Let's see. Okay, so ready? We're looking at cosine. We're going to put our toothpick on cosine. Here we go. When x is 0, slope of cosine is 0. Oh no, maybe you're right. And then moving toward pi over 2, slope gets negative, so that at pi over 2, I think my slope is negative 1. Oh, no. Pink is not looking like the sine graph. Let's keep going. We're looking at slope of cosine. So 0, negative 1, 0. Slope of 0. Slope of positive 1. And at 2 pi, slope of 0. That's not the sine graph. That's the sine graph upside down. So the derivative of cosine of x is negative sine of x. Tell me, wasn't that just a little bit cool? That was a little bit cool. Okay, so now you've got some derivatives that you can start filling in on your table. The derivative of sine x is cosine of x. The derivative of cosine of x is negative sine of x. All right, and the derivative of tangent, I'm not going to take the time to show you the cute little picture, and it would be harder to recognize because you probably don't know what the graph of secant looks like, but the derivative of tangent is secant of x times secant of x. Secant times secant. Looks like that. Or like that. You can either wrap the entire expression in parentheses and put squared on it, or square on the secant. Don't put a square on the x itself. We're not squaring an angle. We are looking at a secant fraction and then squaring that fraction. That's what that represents. Okay, and then so those are great. You're going to have sine and cosine derivatives memorized really quickly. This one you'll be pretty good at. You'll have it memorized probably by the end of your homework. These are harder to memorize. The derivative of cosecant is negative cosecant times cotangent. The derivative of secant is secant times tangent. And the derivative of cotangent is negative cosecant squared. Okay, make sure you've got those copied down correctly before we move on to the examples on the back. In example 1, I've got 2 different problems and it says find the derivative. So not only are we going to use derivatives of trig functions, but check it out. I'm going to have to power rule here, and I'm going to have to product rule. See, I've got like 2 separate functions being multiplied together. I'm going to have to use product rule. I'll call this one 1, and I'll call this one 2. Here we go. I've got y prime equals 1. Let me make a note. We're doing 1d2 plus 2d1. All right, here we go. 1. d2, so I need the derivative of sine. 2. d1. And then I'm going to clean it up just a little bit. And there's not much I can do with it, but I like how the x squared is in front of the trig. I'm going to put the 2x in front of the trig. I don't want any temptation for you at all to multiply this 2x by your angle. Oh, good heavens, no. We would never do that to an angle. So I've got x squared cosine x plus 2x sine x. Then there's no confusion and you won't do something silly to the angle. Next one, I rewrote it just so you can see that it's like a huge fraction. So not only are we going to have to use trig derivatives, we're going to have to use quotient rule. So we get to sing. Woohoo! Here we go. U prime. Whoa. U prime equals big fraction. Here I go. I'm going to start with the denominator. So I'm going to go low, 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 D high, minus high, D low, and I do the derivative of the low, minus high D low. The derivative of a constant is going to be 0. So I've got a you can just kind of cover up the negative for a minute. What's the derivative of sine? Cosine. Throw your negative back on. All right, now let's see what we can do with this mess. You're going to hear me say this. This is going to be typical. We are not going to multiply out our denominator. I really hope that at some point I may be able to cancel something with my denominator. I am not going to multiply that out yet. Can you cancel one of these with one of these? No, because this whole thing up on top is one term, and this is one term. So I've got two terms on top. One of my terms has the quantity. The other one doesn't have the quantity. If you try to cancel one of these right now, you're going to kill a kitten. So I think what I'm going to do is I'm going to distribute this into here, and I'm going to multiply my cosines together. Here I go. Distributing in, so I've got negative sine x plus sine squared x. And then a negative times a negative is plus cosine. Do you see what I see? Do you see what I see? That's cool. Tell me you remember that from trig. Please tell me you remember that from trig. Pre-calc. Okay, so that looks a lot better than what we started with, but I can still go one step further. So if you look at this backwards, if you like switch your terms around, the 1 is going to be positive minus sine x. So this whole quantity up on top cancels with one of these quantities on the bottom. So my final answer is going to be u prime equals 1 over 1 minus sine x. And holy moly, that cleaned up nicely. All right, moving on. The next one. Find equations for the lines, tangent, and normal. So to write an equation of a line, remember, from algebra, geometry, algebra 2, and pre-calc, possibly even pre-algebra. I'm not sure. You should know this by now. To write an equation of a line for the tangent and the normal, I'm going to need the slope of the tangent line. I'm going to need the slope of the tangent line. Bells should be going off up here. And I'm also going to need a point on the line. We'll get there. But for now, let's work on the slope of the tangent line. So to get the slope of the tangent line, we're going to need to do a derivative on our function. So flip back, see what the derivative of secant x is. Y prime is secant x times tangent x. That's the slope of the tangent anywhere. We want our tangent line right here at pi over 4. So I'm going to plug in, notice my notation, I'm going to plug in pi over 4, sub in, sub in, sub in. And then you're going to use those trig skills to figure out tangent of pi over 4. And secant of pi over 4. Well, I wouldn't like doing secant, so I would do cosine and then turn it upside down. So, let's see, cosine of pi over 4 is going to be radical 2 over 2, turn that upside down. Tangent is going to be 1. And so, this is my slope here. This is the slope of my tangent line here. And the cool thing about calculus is you don't have to rationalize your denominator. When you end up with a radical in the denominator, you can leave it. I don't know why. I have no idea why. My theory is calculus is so hard, they don't want to make you do extra work. I don't know. I just made that up. All right, I got my slope of my tangent line. What else do I need? I need slope. Oh, I need a point on the line. Well, doesn't my tangent line, so like toothpick, right? Doesn't my toothpick always touch the function? So the point on the tangent line is also going to match the point on the function. If I want a point on my tangent line, use the point on the function. So, my function is y equals secant x. I plug in pi over 4 into the initial function, and when I sub in pi over 4, I get 2 over radical 2. There's my ordered pair. So, here's my ordered pair. Here's the slope of my tangent line, okay? So this is what I'm going to use for slope. That's what I'm going to use for ordered pair. Here's what they look like. In fact, I'll scoot that over just so we can see everything at the same time. This is my slope of my tangent. That's my ordered pair. Here I go. Tangent line equation is y minus. My y value, m, parentheses, x minus, leave it. Normal line. Again, normal line is going to pass through the same point, but its slope, the line is going to be perpendicular. So I need you to take this slope and do perpendicular on it. So flip it and negate it. Here I go. Normal line. Y minus. Same y value. Different slope.
and they're